In this video, we are going to look at a few examples of finding confidence intervals for population proportions. The first page in this handout is actually a page from the confidence interval reference tables. We're going to have to borrow some material from Unit 5, such as how we construct a confidence interval. So remember, your best guess is what your confidence interval is going to be created around. And for a population proportion, our best guess is the sample proportion. P hat is the notation for sample proportion, and this x and n are the same x and n as they actually were in Unit 2. So x we also refer to as k. So as if we have a lot of letters as it is, now we have one that has two different meanings. But x is your number of successes, and n is your total number of sample size. Now, what we're going to find is that all of these tests that we run come with a set of assumptions that must be met in order for the confidence interval or test to be valid. For testing or creating a confidence interval for a proportion, there are two assumptions that must be met. The sample must be random. The truth is that this isn't able to pass very often because not all samples can be random, but that doesn't mean a sample isn't constructed in a very unbiased way. So if this assumption fails, you're actually just going to keep on going with the problem. In the real world, if this assumption failed, I would go back to the person or people that gave me the data or the problem, and I would ask them how they got their data. So sometimes I say, hey, this data was collected in a way that's very biased and we can't use it. Or I would tell them you took a lot of considerations to really make sure that your sample was representative and we can move on and use the data. Second, there must be at least 5 successes and 5 failures. This one is a deal breaker. If this one does not pass, you cannot find a confidence interval for a population proportion. We'll see in a few units ahead, or a few topics ahead, that proportions are very weak to sample size. So this assumption needs to pass in order to demonstrate that we have even enough data to even think about running an analysis. But as always, the bigger the sample size, the better, but there's going to be a point of the sample size where we reach a level of accuracy, where even if we got a larger sample size, we would still reach similar conclusions compared to the population. Now we actually get to constructing the confidence interval. Proportions follow a z-distribution, which if you remember is another name for the normal distribution, which has this bell curve shape. So every time a problem is focusing on a parameter of a proportion, you're always going to start thinking about this bell curve shape. So next, we construct the confidence interval by taking our best guess and adding and subtracting the wiggle room to it. So my example in the topic 5 notes was if I was meeting somebody at 3 o'clock, I could instead give them an interval where I could meet them at 2:50 to 3:10 instead, which would give them a time frame of, well, I could be a little bit early, or if I'm late, they know I haven't forgotten. I'm just, running a little bit behind as long as it's before 3:10. Well, this E here is the margin of error, and this is how big our wiggle room is for our confidence interval. This last row here is going to be something we're going to refer back to in topic 9. But again, this page here is the first page of the confidence interval reference tables. You will be allowed to use these during the exam. They will be given to you with the test. So you won't need to memorize or write down any of these formulas. However, you will need to know how and when to use them. I'm going to go over this first example. In a Pew Research poll, 70% of 1,501 randomly selected adults in the United States believe in global warming. This is real data. I'm unsure of when this was conducted at this point. So what is the best point estimate for the proportion of all adults in the United States that believe in global warming? So this is asking for the population proportion. We don't know what the population proportion is, but we can have a good guess of 70%. It's a good guess. It's our only guess, and that sounds extremely pathetic, but if this sample was conducted well, it's also going to be a pretty accurate guess. So Pew is pretty popular. They usually try very hard to make sure that their samples are as representative as possible. So I would feel very confident in the results from Pew. Next, we have to check our assumptions. Random will pass because the original problem states that it's normally distributed data. If it does not state that it's normally distributed, you just put an X and keep on going. Again, in the real world, you would go back to the place that you got your data from and say, hey, how is this conducted? Next, we need at least 5 successes and 5 failures. Well, if we want to know how many successes we have, which in this case, since we're focusing on believing in global warming, 70% of the 1501 believe in global warming. So if you were to perform this on a calculator, you actually end up getting 1050.7. Well, we're going to round this one up. And so now if 1051 believe in global warming, then that means everyone else said that they did not believe in global warming. So the rest of those people, 450, are our failures. And not a literal success or literal failure. They're just our, positive and negative version of our answer as far as this is concerned. And this does pass. So part C says, create a 99% confidence interval for the proportion of all adults in the United States who believe in global warming. So I always put 2 lines in this problem. I put a line around 2/3 of the way into the paper vertically, and then I split the larger space in half, although you can do this any way that you wish. First, the point estimate is what everything is based off from, so I usually rewrite this value. Next, I draw the picture that we had created in topic 5. So proportions follow a normal distribution, so they're going to have that normal curve shape. Our best guess is 0.7, so that's going to go smack dab in the center. And then if we have 99%, so we want 99% of our values to surround 0.7, we're going to have 0.5% in each of these tails. 0.5% equates to 0.005. So you need to find the z-score, this moment right here, that separates the tail with everything else. So if you look up 0.005 in the normal distribution tables, you will get negative 2.58 and a positive 2.58 for this upper end since they are symmetrical. So from this, we have all the pieces that we need to find out our error, which is our wiggle room. So the error is the critical value times this square rooted thing. P hat is our sample proportion, and 1 minus P hat is going to be its complement. So it could be Q hat if you wanted to, but I think less notation is probably better. So this is equal to 2.58 times the square root of 0.7 times 0.3 over 1501, which is 0.0305. So we're giving ourselves 3.05% wiggle room in each direction. So 3.05% to the left, 3.05% to the right. And that's what this does over here on these top 2 rows. You don't need to rewrite this form for confidence intervals, but I find it to be very helpful, especially for the first few. Our lower estimate is going to be our best guess minus that error, the wiggle room. The upper estimate is the best guess plus the wiggle room. We end up with a 99% confidence interval that is 0.6695 to 0.7305. The way that we are interpreting these are that there is a 99% chance that our confidence interval contains the true value of the population parameter. So this is pretty good, and this is one reason why we want our assumptions to hold. Because when we make statements as bold as this one right here, we want to make sure that we have the technique to back it up. And part of that is making sure the assumptions for the confidence interval are met. So besides our new formula for the confidence interval for a proportion, we actually have one new concept. That concept is the MVD, which is the minimum verifiable difference. if a claimed value is not inside of the confidence interval, so basically if someone says, hey, I think that 80% believe in global warming, well, 80% isn't inside of our confidence interval. So the MVD, what that does is it tells the person how far they are away from that value they've claimed. So instead of just being like, hey, dude, you're wrong, you can say, hey, you know, based on our confidence interval, you're off by 6.95%. So that's what that MVD is. So it's just the difference between the claimed value and the end of the confidence interval. So the question says, a politician claims that 67% of Americans believe in global warming. Is this supported based on your answer from part C? Well, 67% happens to fall inside of our confidence interval. We don't care that it falls really, really close to a low end. It just is supported by our confidence interval. So all we would say is, yes, 67% is inside the confidence interval, so we are supporting this politician's claim. We don't need to find an MVD here because we're not telling them that they're incorrect. We are actually supporting their statements. So the next two questions here are very, very similar in nature. They are finding confidence intervals in the exact same way. So I'm going to leave this up to you. If you have any questions, as always, please feel free to give me an email, or if you'd like, we can schedule a Skype appointment. No video or camera is needed, but I'm able to share my screen, so I will usually prefer that method.